Hi everybody, this is Nafish. Today I'm gonna go over some of the basics of automotive radar signal processing. Okay, so I'm gonna start from why we are having a certain frequency. Okay, then what are the key radar parameters to design a radar, and then the chip design trade-offs, and after that range and Doppler calculation, profile, ADC data cube, all those things. Okay, but it's going to be a short video. Okay, cause after that I'm gonna in the next video I'm gonna code everything in Python and kind of try to demonstrate, okay, how we're going to build a radar data cube, and then how can we extract the radar range, Doppler, and angle information. Okay, so next video gonna go over Python. This video some of the theories. Okay, so let's get started. So here, automotive radar. Whenever we talk about automotive radar, we hear a frequency 77. Okay, and also we used to hear another frequency band which is 24. Now you will wonder like where from these numbers are coming. So basically, this frequency band is dedicated by the FCC, the committee that governs the frequency allocation. Okay, or ITU in Europe. Okay, so they're the one who allocated this band for automotive radar. Okay, and 24 used to be there, but it's phasing out because there are some advantages of 77 gigs. One of the advantages I would try to mention is like you see the wavelength here is inversely proportional, right, with the frequency. So the more frequency we have, the lesser uh, wavelength or smaller the wavelength is, and the electronic components, the antennas and everything we try to radiate with has to be comparable with the wavelength. So smaller the wavelength, smaller the electronic hardware size. Okay, so basically that's a clear advantage of 77 gigs over 24 because we are going to get smaller hardware, meaning we are saving money on that, right? So there are some other information as well. You can just Google it or go over it, find at your own time. I'll just go into the next slide here. So once we are trying to design an automotive radar, okay, there are few things we have to be clear. Okay, one is like what is the range we want to have, like how far the radar can see. Okay, that depends on this guy right here, the number of samples, and that is kind of dependent on the ADC frequency. Okay, so basically you are transmitting some sinusoidal wave, for example, and getting something reflected back, right? You do the mixing, you get the I frequency, and then you need to sample that, right, from analog to digital domain, right? And so that ADC got a frequency. Okay, so I will like you'll see how these all things are related. So the maximum range a radar can see is kind of see you can see is dependent on two things. One is the frequency of the sampling frequency of the ADC, another is the chip period. So basically, how long you are transmitting this signal for. Okay, the period you are getting. So you see, that's how you get the number of samples, and that is kind of going to give you the range information. Okay, you see the R max. Okay, that is dependent on this number of samples we collect. Okay, now the chip information, the so this is for one chip, right? First of all, what is chipping? We are starting at a certain frequency, and we have certain bandwidth, so we'll just increase the frequency. Okay, so you see it's going up, right? Meaning we are starting at a certain frequency, let's say 77 gigs, and over time we have increased the frequency because you can see the cycles, more cycles, right? You can also have down chip where we start at a like higher frequency, and over time we slow it out. Okay, so these are called chip. It's basically sinusoidal waves, but we are changing it over time. That's why we show it like this. Okay, it's ramping up, ramping down. Now this is one chip, right? From one chip you're going to get like the range information, but you need multiple chips to get the Doppler information, okay, which is the velocity information. So you see here 64, 128, these are the numbers typically you go for. And you know how many targets it can resolve? 64 chips going to resolve 32 targets. 128 is going to resolve 64 targets, meaning if you want to see 64 targets in the environment, you have to have 128 chips. Okay, so anyways, you are going to transmit 128 chips, and the whole time it takes, that's called the time frame. Okay, and that's going to give you the uh, the maximum velocity you're going to get from the radar. Okay, and also it's going to give you see delta v, so basically the velocity resolution. Okay, so this is the two key things, range and velocity. Okay, now these two things are governed by the chip duration. Okay, and as I mentioned below, you see this TC, the duration of the chip, okay, typically from 20 to 100 microseconds. Okay, this is kind of going to determine the maximum range and maximum Doppler. You see the relationships here. Okay, So basically, this is a trade-off. Like if you are going to achieve maximum distance, okay, then you have to compromise this the Doppler, okay. So basically, there is the relationship, and you can just find it out more if you want to dig deeper. But this duration, chip duration, is going to control also the resolution as well. Okay. So moving on, there is also another element or another parameter we are going to focus on. We are going to get the angle information of the target as well. So basically, the radar provides three things, right? One is the range, and there is the Doppler, like what is the speed of the vehicle or the pedestrian or the cycle, and the third one is like at what angle that object is, right? And that's going to give you. We are going to get it from the antennas. So from the virtual antenna element, you see, like you are going to get more resolution. You are going to have more antenna elements. It depends like what is the resolution you would like to achieve. Okay. So in this example or the data cube we are going to make in Python, there we'll show more about it. Okay. So basically it's going to be a 3D kind of data. You can see we'll have range, Doppler, and angle. Moving on here again, kind of showing the steps. Okay. So first of all, the transmit is going to generate the chirp. Okay, meaning you are generating those sinusoidal waves and transmitting it through the antennas. Okay, and basically you are ramping up. Okay, now once it's going to hit the target, you are going to get a return back, right? And from the return you can see this FIF. There are two components. You are going to from the return you are going to get the beat frequency, which has the range information. You see the tau, the time delay. Okay, and also the Doppler information. So basically the intermediate signal, or after mixing, passing the signal through a low pass filter, you will get the intermediate signal. That's going to give you two information. One is the beat frequency, which gives you the range. Another is the Doppler frequency, give you the Doppler information. Okay, so this is step two. The third one is doing the FFT. So you are going to run the fast Fourier transform across these chips, samples, antennas, and going to get all the profiles. Like you're going to get range, Doppler, and angle information. And also, you see the fast time FFT and slow time FFT. What are these? You will hear these terms a lot. So fast time FFT is kind of range information, because for the range information, you are just looking at one chip and the sample time. Okay, but slow time, so it is very fast, right? Like the time it takes to do the job is fast. Slow time FFT is like you're looking across like 64 or 128 chips. Okay, so basically it takes more time than doing this, so that's why it's called slow time. Okay, now moving on here. Here, there are some trade-offs we talked about before, right? So basically, the parameters when you are designing a radar, you have to see like, and you have to get familiar with this. One is the range resolution. Okay, this is kind of like basically the separation of two objects, how finer resolution you are gonna achieve. Okay, now also you need to look into the ADC bandwidth. Okay, so meaning like remember we talked about the intermediate frequency we are getting from the mixture. So basically that needs to be in the digital domain, right? You're going to convert into analog to digital, and that mixture over there. Okay, that for that to perform the job, the ADC needs to have a higher frequency. Okay, like two times higher of that FIF. So basically, it's kind of very challenging with you have to have the selection properly, or else like the burden will be on the ADC. Okay. Now the other thing is like chip duration versus Doppler resolution. This we talked before, like the you see it's kind of, if you want to have more resolution, Doppler resolution, then you are going to sacrifice the range resolution. These are all are kind of interrelated. Okay. Now the update rate, then the power versus maximum range, unambiguous velocity, all these things. This is kind of very interrelated, dependent, and you are going to hear these parameters a lot. So for now, I'm just going to move on. Maybe sometime later I will have much deeper dive on these elements. But here in this slide, just going to briefly give you some overview. Like we talked about the Fourier transform, right? So basically once we do the FFT, we get some profile. So suppose we have two targets in the vicinity. Okay, so basically it's kind of giving you profile. So this is one target, this is two target, this is radar range profile. Okay, and then we are having a threshold here, because we'll say like, hey, if the target is above this threshold, we are going to say this is a target, or else it's a noise. Okay, so there will be challenges. Sometimes the noise will be high enough to go above this CFAR, and that can be a false target. Or sometimes this real target can be missed. So there are a lot of things can happen. Just going to give you some overview on the Doppler side as well. So basically, you know, it's in the Doppler domain. Okay, you will see like there are like two targets here. One is negative, one is positive. Okay, so negative is meaning like it's approaching to you. Positive is just going away from you. Okay, we'll talk more about this later as well. But these are the profiles you get after doing the fast Fourier transform. Okay, moving on here. Uh, so this is the data cube. Basically, what the radar is doing. It's collecting um, the data. Like you're sending one chip, right? Then you are getting some data here, some samples. Now you are going to send 128 chips. You are going to gather data here, right? And then for like say we have four antennas, you are going to receive all those data in four different antennas, right? So basically, if you see here, what will be the size of the data cube? Okay, here is an example. Here is you see, we are sending out 256, sorry, 128 chips, and from each chip we are going to get 256 samples, and then we have 16 elements. So this is the total size of the data. Okay, and